Here's the algorithm. Though it's quite general, it will help to fix your mind on the example that we are working on. So S is the state space. In our example, that's a set of all decoders. So it's a set of all permutations of the alphabet. Pi is a distribution on this space. In our example, that is the set of, it's the distribution of scores, normalized scores. And that is an intractable distribution because the state space is huge and you actually can't normalize the scores. What you want is not the entire distribution, but the mode of the distribution. In other words, we want the decoder for which the score is the highest. And what we're going to do, for reasons we've discussed, is try to construct a Markov chain that has this particular pi as its stationary distribution. Now, what does it mean to construct a Markov chain? We have to specify its transition behavior. And we're going to construct it in such a way that this pi and the p that we construct together have detailed balance. And if they do, then we know that our specified distribution pi is the steady state distribution of the chain that we have constructed. So how are we going to do that? Well, it's a good idea to remember that our chain is going to move from one decoder to another. And you have to start somewhere. And so the algorithm starts like this. You've got to construct a transition matrix. Start with any transition matrix at all, almost. Start with any irreducible and here's an important condition, symmetric transition matrix, which I will call Q, on your state space. So in our particular example, the state space is all the decoders. Q is just any transition matrix on the space of all decoders. As long as it is irreducible, you can get from every decoder to every other decoder eventually by following some path. And it's symmetric for reasons that will become apparent when we start doing some calculations. Now, Q can be very simple. It can be just, I will move from one decoder to the two nearest ones with probability half each. That would be fine. That will work as a symmetric decoder. But of course, that's not got anything to do with the pi that we started with. So we have to introduce that pi somewhere. So let's now describe the transition behavior of the chain that we're constructing. So supposing your chain is at decoder I, then how do you move at the next step? You go to the ith row of Q. You just pretend that Q is your transition matrix. So row I of the transition matrix Q gives you the conditional distributions of the conditional distribution of where you would move if you were just using Q. So do that. Pick a state according to row I of Q. Q has got nothing to do with anything. It's just something you made up. Nevertheless, what we say is that Q proposes a move to J. Right? So this transition matrix that you came up with says, okay, you're at I, move to J. Now you get to decide whether you're going to accept this proposal or not. And your decision can involve your criterion. And your criterion is that at every stage you would like to move to a decoder that has a higher score than the one you're at. And so at this point you consider the ratio of the two scores. So this thing is called the acceptance ratio. Rij is going to be pi at the proposed decoder relative to pi at the current decoder. And remember, we want to move towards bigger values of pi, right? Higher scores. So this odds ratio we can compute because this is just the one score divided by the other score. The normalizing constant is the same for both cases, so it cancels out. This is the ratio of the two scores. So what shall we compare this ratio to? We'll compare it to 1. Now, if the ratio is at least 1, then the state that Q has proposed, the state J, decoder J, is at least as good as the one we have got. It's at least as good as I. So if this ratio is greater than or equal to 1, then move to J. If the ratio is less than 1, then the matrix Q has proposed a state that is worse than the state we're currently at. For us, it has a lower score. And so the temptation is to not accept the proposal. The temptation is to just stay put at I and play again. Except that this risks spending time at local maxima. And so what the algorithm does is it puts in a little bit of additional randomization to give us a chance of getting out of local maxima. So it says if your ratio is less than 1, so if Q is proposing a worse decoder, you toss a coin. And not a fair coin. A coin that lands heads with chance Rij. Now this Rij is less than 1, so that is a chance. And now you look at this coin, either lands heads or tails. If it lands heads, you move to J. And if it lands tails, you stay at I. So this is a complete description of transition behavior. So let's just make let's just look at the sequence, and then we'll talk about what's going on. So you start at decoder I. Your matrix Q then goes to its row I and proposes a move to J. You then look at whether that state J is better or worse than the state I that you're in right now by comparing the two scores. And your algorithm says that if the new state has a higher score, just go there. Or even if it has an equal score, just go there. If it has a lower score, then you have a little dance to do. You toss a coin and make a decision based on the toss of a coin, and the decision is whether you accept the proposal to move or whether you stay where you are. Now, it's all very comprehensible, except this last little bit, we have to see what's going on. Okay, so I want you to look at the condition Rij less than or equal to 1. Remember that this Rij is going to be the probability of heads. I'm sorry, I misspoke. Rij is strictly less than 1. So supposing Rij is 0.9. So this coin is hugely likely to land heads. So you're hugely likely to move. Does that make sense? Well, if Rij is 0.9, then your pi j is very close to your pi I, right? So the two decoders that you have are pretty close in score, right? So it just sounds like a really good idea to move. In case you are at the top of a tiny little local hill, maybe if you move to somewhere a little bit lower, you can see the top of the mountain that you are trying to reach. If Rij is, say, 0.1, then the decoder J is much worse than your decoder I. So you toss that coin that lands heads with chance 0.1. It's not likely to land heads. It's much more likely that it's going to be tails and you're going to stay at I, which is kind of what you want to do. So this makes complete sense, this algorithm. It is a very, very simple algorithm which starts with any transition matrix Q at all, as long as it's irreducible and symmetric, and then uses that and a comparison of the scores of two states with this additional coin tossing randomization to make the decision whether you move or not. And it is brilliant in its simplicity because it just works. It is very easy to show that this will produce a chain that has our pi as its steady state distribution.